everyone, welcome to our channel Knowledge Hub. Friends, subscribe to our channel and click the bell icon for the latest update. आज हम लोग प्रिंसिपल ऑफ प्रोग्रामिंग लैंग्वेजेस की क्लास करने वाले हैं जो कि क्लास नंबर 10 है एंड होपफुली अगर ये 1 घंटे से ज़्यादा एक्सीड नहीं करता है तो दिस विल बी द लास्ट क्लास ऑफ प्रिंसिपल ऑफ प्रोग्रामिंग लैंग्वेज वे विल completed the unit 5 which is the lambda calculus, and this is the first class of lambda calculus as well. And this is in last 9 classes we had completed the unit 1 and unit 2, unit 3 and unit 4. This is starting with unit 5th which is your lambda calculus. So here first of all we have to know something related to about lambda calculus, what it is all about and what were the topics we'll discuss here. Before starting with this, first of all, it's a huge request from my side to all the viewers. Please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In the terms of the lambda calculus provides a model for describing a function and their evaluation, as well as the general form of the lambda expression is to be written as lambda x dot m, and the variables in the lambda expression that can be free or bound as well, and that is the several rules, which is the conversions that are present for manipulating the values, the variables in the functions of the lambda expression as well. So we'll discuss about the lambda calculus. What is lambda calculus? Write down its uses. So let's go ahead to discuss about it in a detail, which is lambda calculus. In the term of the lambda calculus, that it is a fundamental theory of the functions that provides the rules for defining and manipulating the functions. Lambda calculus is a mathematical method for expressing computations by functions and is used for studying functional programming languages concept, and it is simple, unconditional syntax and semantic, useful for studying the theory of functional programming languages and understands its commodities, commonalities as well. The general form of the lambda calculus has been represented in the form of that, as I told you about it, which is your lambda x dot m here, and it is known as a lambda function with a parameter x and a body m, and that the symbol this dot symbol that is used to separate out the parameter from its mapping rule. An example of lambda x dot x abstract x, that is a function for that maps the value of x with x minus x, that the lambda expression that can be applied here, and in the same cases for its evaluation that has been taken place. So the lambda calculus is used to create procedures, and it takes one of the following form, and we'll be having a form here. The first we have is your identifier, or the that is identifiers or axioms. So in this term of the identifiers and in terms of axioms here, it can be constant, variable or a function, and constant are treated as function that gives a constant result as well. The second we have is your abstraction. In the term of abstraction, an abstraction is one augmented lambda function that has been represented by the lambda x here, that is an expression, or the lambda x e that has been represented here, where x is an identifier or the parameter and e is a lambda expression, and the function is evaluated by substituting the x into the e here. The third we have here is that is your application. In the term of the application here, that an application that represents more than one lambda expression, and that is in the form of x, e1, e2. Here it represents the application of e1 function e1 to the value of denoted by the e2 here. Now we'll talk about more on the detail, that is to describe the operations performed on lambda expressions here, and that what we have to discuss here as well. So let's go ahead, which is your operation performed on lambda expression. So the operations performed on lambda expressions, that we'll talk about it. So here in the same case, and lambda expression that have only one reduction operation. If fa is a lambda expression, then f equals to your the function is equals to lambda x dot m as well, and then a may be substituted for all the free occurrence of x in m as well. And the same references, this can be written in the form of, we can say that here it will be represented in the form of lambda x dot ma, which is will give you m dash here. And this operation is analogous and to substituting an argument for a formal parameter in a function call. An example of the lambda expression, that reductions that it follows here, and that will be in the form of like lambda x dot xy that tends to y, and lambda x dot xy y that gives you y and y, and here lambda x dot xy lambda x dot x, which tends to give you lambda x dot xy, and that is tends to y here. So in the same case, with the same reference towards this, if I'm talking about here, that is your lambda x dot x comma x, that is lambda x dot xx, and that is your tends to give lambda x dot xx lambda x xx here, and that gives you so on. So this is an expression of what it will give it here. And in the same cases, and the reduction operation that does not always results in lambda expression, that is simpler than the original expression, and the fourth example does not terminate as well. In any lambda expression, there are the two standard approaches towards the reduction. The first is to reduce the innermost left term first, and to reduce the outermost left term first. So let's write it down as well. The first is reduce innermost left term first, and the second is that to reduce, that is outermost left term first. In the same case, the example is in the lambda expression that we had represented here, and that the outermost term is the entire expression, whereas that the innermost term is to be like lambda x xx and a, and that the two reduction sequence that are possible here in the terms of it as well. In the same cases, for the outermost reduction first and the innermost reduction first, we'll take an example of one of the thing here, that the equation we have lambda y and that is lambda x dot xx a. This is an expression here, so we'll solve it out for in the reference toward the outermost first and the innermost first, so that you will be able to understood how you have to solve it out, all these things. So for the outermost first, and this is for innermost first. So in the same expression, so we'll solve it out for both of it, and that is for the outermost, what we'll do is lambda y dot y, and that is lambda x xx a, then the expression close, then it will give lambda x dot xx a dot, and that is your lambda x dot xx, and that is here. And then after that it will be lambda a, and that is closing. For the innermost here, that the expression we'll be having is your lambda y dot y, and that is a closing, then lambda x dot xx dot a here. And after that we'll be having lambda y dot y a, that is expression close, and then we have a, and that is closing here as well. So in the same cases, now we'll go ahead to discuss about it the another one, which is to express here, and that what we have to even do and to consider about it, and that is to explain the lambda calculus as a logical model of computation, that what we have to discuss here. Lambda calculus as a logical model of computation. For that, we'll have to solve it out and we'll have to consider about it. In this in the reference towards this, we can say that the lambda expression that are used to model the predicate calculus, using the predicate calculus, and we can model the integer, we model the boolean values as a lambda expression, and that is true, that is t is defined for that lambda x lambda y dot lambda x as well, and for the false is defined as lambda x lambda y dot y as well. Following the properties are of the true for these objects we have, and that is if tp and x, that will tends to the property that will write it down, and you can get to know about it as well. The first property we have is tp, that tends to p, that is, you can say that tp q, that tends to lambda x dot lambda y dot x p q, and that tends to lambda y dot pq, that tends to q here, that is p. Okay, so the other thing is in the term of it, that what we have, the another property is termed as, which is fp q, that tends to q, and that is fp q, that is tends to lambda x dot lambda y dot p, and that is q, and that gives you lambda y, and that yq tends to q here as well. So here for that, for the given boolean function integer, that can be, and for 0 that lambda f dot lambda c, which dot c as well, and for 1 the lambda f dot lambda c, that is fe, and for the lambda 2 that is lambda f lambda c and f of fe, and that is of lambda 3, that is lambda f, which is lambda c, and f that is e, that c is a 0 element here, and that is f is a successor, and that is to add up 1, and the function that applied sufficiently to the c element, that the arithmetic operation that can be defined as integer n, that is written as the lambda expression na, and which is lambda c in the terms of applying reduction to it, and we'll get it out as well. Let's go ahead to discuss about more detail about it. What are the free and abound identifiers here? Free and bound identifiers. In a free and abound identifiers, here an occurrence of an identifier x in an expression is bound if it is appeared in the formal parameter, or an identifier x in an expression is bound if it is within the scope of an expression in which it's involved. That is that the identifier x has a role of delta x of m, and a pure lambda term without the free variable is called a closed term, and or that is combinator. And a reference that is not bound to a formal parameter in the expression is said to be a free identifier. Example is that the lambda expression we have delta x of m, and for where delta x dot x plus that y, where m is equals to x plus y, and that has been represented here as well. So here in the references of the expression that is x plus y, we'll just go ahead with the equation as well. lambda x dot x plus y, where m equals to x plus y, and where delta x dot x plus y expression we have, which is your 5 equals to 5 plus y here. So that is the references. X is an expression of x plus y that is appeared in the parameter, and there x is a bound identifier as well, and they reference y as a free because it is not in the scope of any expression, and free identifiers are the problem in the lambda calculus, and the bound identifier in a scope or that is a local entity, while a free identifier is a global entity that is provided by the outer scope, in which first scope is embedded. For example, lambda y dot lambda x, which is x, y, z here. So where x and z are the bound identifiers, and in the term of the delta x, lambda x and lambda y and lambda z respectively. So the free identifiers may not be named without changing the value of an expression within which they occur, and in a valid complete lambda expression, all identifier occurrence must be bound as well. So let's go ahead to discuss about another question in a detail here. That the question is to explain the rules for manipulating the value variables and functions in the lambda calculus expression. So that what we have to discuss here. That is rules for manipulating the values, variables, and functions in a lambda calculus expression. So in this, the first we have here is your alpha conversion, which is your alpha conversion here. In the alpha conversion, we'll talk about it, and that is in this that it refers to the renaming of the bound variables, and this rule allows user to change bound variable as long as the new name cannot conflict with any other identifier name in an expression, and that the expression we have is your lambda x dot m that gives you lambda y dot m, which is of y of x as well, and that that is your alpha, that provided that y does not occur at all its expression where y of x that indicate a new name and an old name here, and that example of this we have here is to be as follows: lambda w lambda y dot yz w, that will give you lambda x dot lambda y dot yz x, and that is of x of w here. So this has been represented in that. Here the variable w is changed to x in the lambda expression here. The second we'll talk about it, which is your beta conversion. Which is your beta conversion. In the term of beta conversion here, that it refers to the beta reductions and the beta abstraction. This rule describes a function application mechanism in which the actual substitutions of the parameter that are carried out, and that is means lambda abstraction is applied to a particular argument, and the beta conversion that can be specified to, which is lambda x expression 1 and expression 2, that is tends to expression 1 and expression 2, in which the substitution of x in an expression 1 is carried out, and according to the rule of a safe substitution as well. Talk about the third one, which is your Eta conversion, that is the third one. Eta conversion, which is represented by and that is your n conversion. In this, that it refers to eliminating the redundant lambda abstraction. This rule can be simplified to in the form of, that is your lambda x dot expression x tends to n expression. So here in the same case, that which require that x have no free occurrence in the expression, so as any conflict is avoided, and if expression stands for the predefined function, the rule remains the valid as an expressed. And that is in the same case, if I'm taking an example here, you can go through with that as well. So here in the same case, that is lambda x dot square phi x tends to square 5, this is equals to 25. You also know the 5 square is 25 here. Now we'll go ahead with the detailed about it, and that what we have to discuss here in the same case, that is the another one, which is your the fourth one, and that is the fourth one we have is your gamma conversion. In the gamma conversion, and that the gamma conversion has been represented in the form of, which is in the form of gamma conversion. So in this, that it is associated with the predefined values, predefined values in a function, and this rule can be simplified to that is your the function xy tends to gamma function, and that is of xz here, sorry xy. So here that in the words in the if lambda calculating, that is the calculus has predefined the constant and the function, example like add, subtract, square, so that rules associated with those predefined values in the function that are called gamma rules as well. In the same case, we'll take an example here that to solve it out. So here that we have, that is your add 5 3, that is your you'll get add 5 comma 3 is equals to 8, 5 plus 3, that is equals to 8 here. Okay, so now we'll go ahead to discuss about the another one, that is in the terms of it, which is the explain recursion in lambda calculus. Recursion in lambda calculus. In this recursion in the lambda calculus here, that the recursion is the definitions of a function using the function itself, and that consider for an instance of the factorial function that is recursively defined here. And for that we can say that here as your fn that is equals to 1, or if n equals to 0, then of course the n and f that is n minus 1, and if n is greater than 0 as well. So in the same cases, for if a lambda calculus for one cannot define a function which includes itself here, and that we define a function g which takes the function f as an argument and returns another function that takes n as an argument, and where we can say that that has been represented in the form of, which is g lambda fn lambda if n equals to 0 and n comma f n minus 1 if n is greater than 0. So here that the function that g returns is either the constant 1 or n times that the application of a function f to n minus 1, and using the that as a 0 predicates and a Boolean and an algebraic definition that the function g can be defined in the lambda calculus, and f must be expanded to g of f, and that is this calls to the g will then expand to the factorial function, and that calculate down to the another level of recursion as well. This kind of a function where f equals to g of f, that is called a fixed point of g, and it can be implemented in the lambda calculus using the paradoxical operator or a fixed point operator, and is represented by as well, and that is represented in the form of y equals to lambda g dot lambda x dot g f xx, and that is lambda dot x dot g x x here. In the lambda calculus, that y of g is a fixed point of g as it expands to g of y of g as well. So let's go ahead to discuss about more in the detail about it, and that is to discuss here, which is another question, that is to explain beta equality here. So let's go ahead with that. In the beta equality here, that the key axioms of the beta equality is to be as follows, that has been represented in the form of lambda x dot m, and that is equals to b, that is your beta n of x m here, so that beta axiom. So thus here in the same cases that has been represented on that the following axioms that allows the bound variables to be systematically renamed, and in the same cases that has been represented that provided that z is not a free of m, that is of alpha axioms, and thus delta x dot x that beta of delta y, and that is your lambda y and y as well. So that is each rule of the beta equality must be true with any notions of the equality on the terms, and we'll talk about idempotence here. In the term of the idempotence here, term m equals itself here. The second we have here is that is your commutatively, and that is your commutativity. In the commutativity here, that is if m equals n, then conversely n must equal m here. The another one is your transitivity. In the transitivity here, if m equals n and n equals p, then m equals p to power 2, that the replacement of the equal for equal is formalized by the two congruency rules. If m equals to beta of m and n equals to beta of m as well, then mn is equals to beta of mn here. So the furthermore we'll talk about it. If m is equals to beta m, then delta x lambda x m equals to beta of lambda x m as well. So let's go ahead to discuss about the another one, that what we have to discuss here, and with the help of an axioms and the rule for the beta equality, you have to prove S1 II that is equals to beta of lambda z dot lambda zz, so that we'll have to represent it here as well. So in the same cases, we'll go ahead here. You have to prove what is equals to beta lambda z dot zz, and in the same cases that S11 is written as Si and Si, as that is reversed of the lambda x by z dot Lz, where I is reversed for the delta lambda x dot x, and that is of Si here as well. So here we'll talk about it, that that has been represented here, xyz dot xz, and that is yz x dot z lambda x dot x as well. And we use alpha axioms to rename bound variables, and for that we have your lambda x yz dot xz, and that is your yz as well, and that is your has been represented here. The second copy of the lambda xs is not renamed as we had represented in that the first change of the structure, that the term is due to the beta axiom, and the right side of the form that substituting the delta lambda u dot u in the x places. So we can say that x y that is represented here, that is lambda yz dot lambda u dot u z yz lambda v dot v, and which is equals to beta lambda yz, and that is dot z yz lambda v dot v, which is equals to beta lambda z dot z lambda v dot v z, and that is equals to beta delta lambda z dot z z. So now we'll discuss moreover related to about the another one. This is describe the charge Rasa, that is your theorem here, and that what we have to discuss here. So let's go ahead with this as well. In the same cases that we'll talk about, describe the charge Rasa theorem as I told you about it. So let's go ahead. Charge Rasa theorem. In the charge Rasa theorem, if I'm talking about here in this, that as I told you about the axioms and rules. So for all the pure lambda terms, that is m, p, q, and if m and p tends to m and q, then of course there must be exist a term r that such that p tends to r and that q tends to r as well. The Judge Rasa theorem that says that the result of a computation does not depend on the order in which the reductions are applied, and all the possible reduction sequence progress towards the same result. And the Judge Rasa theorem that extends to any of the two beta equal terms, that is if p tends to q, then there must be exist a term r such that p tends to r and q tends to r as well. This theorem can be stated as in the following way, which is your yf equals to lambda f fxx lambda x dot f xs and then f. So that tends to here the beta, if I'm talking about with this, just beta here, that is lambda x f xx, that is lambda x f xx here, and that even tends to here, that is the other one is your beta, which is tends to f xx, that is your lambda x dot f x lambda x dot f xx here, and that tends to f of yf as well. So here this form shows that how term that that your gamma fp reduces to f, that is your yf as well. So now we'll talk about in a detail, that is another one, which is your typed lambda calculus, that includes the notations of the data types as well, and the type system that prevents the occurrence of the execution error as well. And we will talk about the unique terms that are that is typeable and certain conditions that need to be fulfilled for the type S and T in order for it to be called either a join or a meet as well. In the same cases, we'll discuss about what do you mean by a typed lambda calculus. Typed lambda calculus. So in the typed lambda calculus, where the abstract syntax of a simply typed lambda calculus is defined to be as in the form where x is denoting the variables, lambda x that is denoting the abstraction, and t is denoting the application, true is the constant true, false is the constant false, and if t then t else t, that is a conditional. So talking about the typed lambda calculus, that includes the notations of the data types that invoke in the lambda expression. Example like an identity function from the integer to integer that can be written as in the form of lambda x int x. So here that this variant of lambda calculus that has rules for determining the type of the lambda expression and the type that constants that are valid expression that must meet, and the type lambda calculus is a proper subset of the class of untyped lambda expression and introduces the rules and the constants where the typing identifiers means that every occurrence of an identifier that must be a given type and given a type as well, and the typing rules that refers to the defining the type of a general lambda expression and the type of an abstraction of lambda x that tends to alpha here, where expression this tells that the alpha tends to beta, and where beta is a type of an expression and the type of an abstraction lambda x, that b expression beta is expression and expression 2 is that we can say that in the same cases where lambda alpha tends to beta here, and where the type of expression 1 is alpha tends to beta and the type of expression 2 is alpha here in the same cases. So let's go ahead to discuss about the another one which we have to discuss, that is to describe the type system in detail. Type system. In this talking about it in a type system, where that the fundamental purposes of a type system that is to prevent the occurrence of execution error during the running of a program, and the type system that act as an aid to modeling by a provision of a set as irregular interpretations of patterns, and a type of system that provides the mechanism by which the inappropriate application of an operation is prohibited. Thus, a type of a system is regarded as a provider of both modeling and protection within a programming system. A language whose type system prevents any operation which violates its modeling facilities is to refer to be as a strongly typed language, and before the strong typing is enforced in a programming language, the designers must be confident that the modeling provided by the type system is adequate for a language purpose, and if the type system modeling is inadequate, then the programmers are forced to use the inappropriate type models as well. An operation which violates the model that provided by a type system that may be detected at any time before the operation is executed, and it is desirable to detect such error as early as possible due to the two reasons. And the two reasons we have, the first is your program safety, the second is your program efficiency. In this, the type system that are viewed as mechanism which impose the static safety constants upon a program, and the data manipulated by a programming language that is governed by that language type system as well. We are now talk about explain the typing the relation and rules for typing abstraction as well. So here the typing relation and the rules for typing abstraction. Here we'll go ahead. Typing relation and rules for typing abstraction. In the same case that the typing context that is I, that is a list of a variable and their types, and the comma operator that extends here, and that by concatenating a new binding on a right side, and to avoid the confusion between the new binding and any binding that may already appear in this. So we require that the name X that we choose in node so that it does not already appears in the DOM, and that can be just to be thought of in a finite function from a variable to their types. And following this will be write a DOM, and that is the set of the variables that is bound by with it, and which is represented, the DOM is in the form of like this, and that is of DOM of X, and the type T that is associated with an X in DOM here. So the rule for typing the abstraction actually that has a general form, and that will be represented in the form of DOM X T1 t2 t2 upon dom lambda x t1 dot t2 t1 tends to t2 here. So here where the premises adds one more assumptions to those in the conclusion, and a variable that has whatever type we are currently assuming it to have it, and that is in the form of x t belongs dom upon dom xt here, and that is a rule for application we have. For that we have here t1 t2 t1 2, so that if t1 evaluates to a function mapping argument in t2 to result in t1, and under the assumptions that the term represented by its free variables that yield the results of the type associated to them on the DOM, and that is, and if the t2 here where in the same cases that evaluated in the t2, and then the result is applying in t1 and t2, that will be a value of the type t1 as well. We have a typing rule for each of the individual construct in our simple language, and to assign the types of the whole program we combine these rules into a derivation tree. And for example, here a derivation tree that is showing that the term of that bool, that true, has been a bool in an empty context, and in the same variable we have. Now we'll go ahead to discuss about the another question, which is write down the lemma of inversion of the typing relationship, that relations that we have to discuss here. So let's go ahead with that. Lemma of inversion of the typing relation. So in this, the first we have if x r, then so that belongs to DOM. The second we have if DOM into x, that is t2 t1 r2 tends to r1, then r2 equals to t2 and DOM x t2 t1 r1. The third we have here is if DOM t1 t2 belongs to r, then there is some type t2 such that DOM t1 t2 that belongs to r and DOM t2 that belongs to t2 here. Now the fourth one we have here, which is if DOM true r, then r equals to bool. And the fifth one we have if DOM false r, then r equals to bool. And the sixth one we have, which is if DOM if t1, then t2 else t3 r, then which is your t1 bool DOM t2r and DOM t3r here. This is in lemma of inversions of the typing relation here. Let's go ahead with the further one which we have to discuss, the prove the uniqueness theorem here. I will discuss about the uniqueness of theorem here. In the uniqueness theorem, in a given typing context, that is your DOM and a term T with a free variables, or in the domain of DOM that has at most one type, and that is if the term is a typeable, and that is then its type is unique. And the proof of the uniqueness theorem that can be stated as, and now we'll prove it that as well. Suppose that the DOM that belongs to T and that is a S here, so that we show that the induction on the derivations about it, that is where S is equals to T, where the case T where we'll discuss about it. And for that, T equals to X with X is not DOM. So according to the inversion lemma, that the final rule in the any derivation that DOM here, that must be a T variable where S equals to T, and that is for that we have case T A B S, which is your T equals to lambda y T2 dot T1, that says that T equals to T2 that tends to T1, and that is your term y T2 T1, that is T1 here. So by the inversion lemma, that the final rule in any derivations of this, that must be able to T ABPS and ABS, and that is the derivation that must be have a subderivations with a conclusion, that is DOM comma y, and that is with S tends equals to a T2 that tends to S1 by the induction hypothesis on it. And in the same cases, by the induction hypothesis, that the subderivation with the conclusion with that will be having DOM by T2 T1 T1 here, and that we can obtain S1 that equals to S2 S1 equals to T1 from the S equals to 2 is S equals to T, that is immediate here. Now we'll discuss moreover related to the another thing, that is to describe the relation of subtyping. For the relation of subtyping we'll discuss here. So here in the relation of subtyping, that the subtyping relation is defined for the types that is having similar structures, and the subtyping relation that should be a reflexive and a transitive as well, and that will be represented in the form of DOM S less than U, DOM U less than, that is your T here, and that is upon DOM S less than T as well. So these rules follows directly from the that is intuitions of the safe substitutivity, and that the remainder of the rules that is defining the subtype relation that concerns the behavior of the specific type constructor as well. And in the same cases, for the required type, we have seen that we want to consider the type S, where the type S is equals to like K1 colon, which is your S1, and Km, and of course the Sm as well, and that to be a subtype of T, which is equals to I1, and T1 that is still In, that is of Tn as well. if t is obtained by dropping field from S, and that the representation we will be having. That is less than. And as well, so that is here, that is representing the width, and we can also the type or allow the types of the common fields to differ, and so long as they are types and S that are subtypes of their type, and T as well for each that belongs to here, and that also it makes the sense to ignore the order of the fields in a record, since the only thing that we can do with the record, namely that the field projection, which is insensitive to the, that is insensitive to the order of the fields, and for the function that the rule we have, that is we allow a function of one type that to be used where the another is expected, as long as none of the argument that may be passed to the function by the content that will be surprise it that t1 is less than s here, and none of the results that it returns with the surprise the content, where in the same cases that is your the s2 is less than the t2, and that the sense of the subtype relation is reversed on the left of the arrow, and this rule is sometimes referred to as a contra variant arrow rule for this reasons as well. Now we'll go ahead to discuss about it, which is with the help of a lemma proof the soundness of the completeness of algorithm subtyping, that what we have to explain here. So with that proof we have to use the algorithm subtyping here with the help of the lemma, prove that the soundness of and completeness the algorithmic subtyping. So here the algorithmic subtyping relation is the least relation that is closed under the following rules. Here the algorithmic subtyping that is tends to the algorithmic subtyping, which is the representation is a different representation here, and that is the arrow and the top has been represented here. So let's go ahead with the soundness and the completeness of the algorithm. We'll be finding it out is in the form of less than t if s at here. Now the proof of the algorithmic subtyping that can be written in the form of, that is your subtype s comma t if t equals to top, then true, else if s equals to s1 that tends to s2, and t equals to t1 that tends to t2, then subtype t1 ts1, which is your subtype s2 t2, else if s equals to aj sj, that is I belongs to 1 till m, and t equals to I1 that belongs to t1, that is I belongs to 1 till m, then for all I belongs to 1 till n, find j such that a of j is equals to l of I, and check subtype sj tj sj and ti, else false. So this is a representation, this is a proof of algorithmic subtyping that can be written in the form of here. Now we'll discuss the other question, that is, what do you mean by algorithmic typing relation? In the algorithmic typing relation here, in this, that the algorithmic typing relation is the least relation that is closed under the following rules, and the algorithmic typing is to be turned as in the form of that tends to T, where T belongs to DOM upon DOM x d, and which is tends to DOM x t1 t2, and that is t2 upon DOM lambda x t1 t2 t1 tends to t2 here, t1 goes to t11, that tends to t1 to DOM tends to t2, and that is your t2 belongs to t2 that is belongs to t11, and that is upon DOM that tends to t1 t2 and t12, where in the same case for each here for each I DOM tends to t1 that is belongs to t1, and upon DOM tends to I1, which is equals to t1 till tn, and I1 left t1 till in and tn here. So for that is represented here, and that is your TR-PCD. And the theorem for the soundness of the algorithm typing relation is stated here as we had done. The ordinary typing relation that can be used to assign many type to a term as well, while the algorithmic typing relation that assigned at most one, so a straightforward converse of the soundness of algorithmic relation is not going to hold, and instead we can show that if a term T has a type T under the ordinary typing rule, then it has a better type S, and under the algorithmic rules, in the sense that S is less than T. In other words, the algorithmic rules that assigns each typeable a term that is smallest possible minimal type, that's the minimal typing theorem that can be stated as here. So here we'll discuss about the another one, which is your what are meets and join. So what are meets and join here? A type J is called a join of pair of the type S and T if we say that S is less than that J and T is less than that J as well, for all the type U and that is belonging towards it, and a given type that lambda calculus is said to have a joins if for every S and T there is some J that is joined for S and that T under the DOM as well. And similarly a type M is called a meet of S and T if they belongs to where in the case S and that is belongs to M less than T as well. So for all the types here, and then a pair of the S and T that is said to be a bound below if there is some type of L such that L that is less than S and that is less than T as well. And a typed lambda calculus is said to have a bounded meets if for every S and T such that S and T are bounded below and there is some M that is meet of S and T as well. So here we had end up with unit 5 of principle of programming languages, which is the end of principle of programming languages subject we had covered up. So first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. In talking about terms of it here, that is we had covered up the unit 1, which is the introduction part here. That is the introduction, the role of the programming languages, why study programming languages towards the higher level languages, programming paradigm, programming environment, language description, syntactic structure, language translation, issue programming languages, syntax, stages in translation, formal translation model as well. We will talk about in the unit 2 here. So here in the unit 2 we'll discuss about language properties, which is language properties, modeling language properties, elementary data type, encapsulation, inheritance, sequence control, subprogram control as well. In unit 3 we had covered up the unit programming paradigm, which is the programming paradigm, imperative programming, statement type, procedure activities, object oriented programming, grouping of the data and the operations, object oriented programming, functional programming, elements programming in a type language, programming with list as well. In unit 4 we have to cover up with the other programming paradigm that comes under in it, that is the other programming paradigm, logic programming, concurrent programming, network programming, language description, semantic methods as well. And in unit 5 we have to complete with the Lambda Calculus, that is we had completed in this class, which is the Lambda Calculus, introduction to the Lambda Calculus, simple typing and subtyping as well. So first of all, it's a huge request from my side to all the viewers, please go through with the subscribe button and please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. We had completed the principle of programming languages, and soon we'll complete with the data warehouse and data mining, and we are doing with computer graphics as well, data management and database management and system as well, and managerial economics as well as the reasoning and quantitative aptitude we are doing here as well, so you can go through with that. So please like, share and subscribe our channel so that many and maximum people can get the information at once, and even though you can also enjoy the video as well. Thank you, hope you enjoy this video. If you like this video, please give a thumbs up and give a suggestion on a comment box. Thank you.